Hello students, today we are going to see the magnetic torque and the moment. So in the last class we have seen the force experienced by the charge and force experienced by the line current and force between the two charges. Now we are going to see the magnetic torque. So whenever we place a current loop inside the magnetic field, it experiences the force. That force leads to torque. So we have considered a force on a current loop in a magnetic field. So we can determine a torque on it. The concept of current loop experiencing a torque in a magnetic field is very important to understand the behavior of motors and the generators. If the loop is placed parallel to the magnetic field, then it experiences force that tends to torque, that tends to rotate it. So a torque is indicated with capital T. The torque is indicated with capital T. And torque is a mechanical movement of force. It is a vector product of force and the movement arm. That is capital T. That is torque is a vector. So torque is equal to, this is your momentum and your force. So this is a vector and this is also one vector. So this is your torque. So torque is equal to momentum plus force. What will be the unit for this torque? Units of your torques are Newton per meter. Newton per meter. So let us consider one current loop. Let us apply a force. Let us see how will be the torque. So let us consider so this is one current loop. So which is placed inside magnetic field. Let us consider this is the magnetic field lines. So these are all the magnetic field lines. So this is your point 1, 2, 3 and 4. So this is your magnetic field line B. So while discussing the force current, that is the force experienced by the line current, we got F is equal to, that is F is equal to something line integral over I dl cross B, IDL cross B. This is a generalized equation for the force experienced by the line current. This is your line integration. So this is 1 to 2 is one line, 2 to 3 is one more line, 3 to 4 and 4 to 1. So total it is of, so the width, the distance from 1 to 2, that is width is W and the height is L. The height of this point is L. So L is from 2 to 3, it is the length of L and its width is W. So by using this, so here we have considered a closed line integral, that is of closed current loop we have considered, that is of 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So here there is existence of your 4 integrals. So the final force is equal to the integration from 1 to 2 IDL cross B plus from 2 to 3 IDL cross B plus 3 to 4 IDL cross B plus 4 to 1 IDL cross B. From 1 to 2, let us consider this is your current direction. So let us consider this is the direction of current. So if you observe, it is a IDL, DL versus this is the current versus B is a cross product. So if you consider from 1 to 2, the current direction is, this is the current direction and this is your magnetic field direction. So there is a 180 degree phase shift. So in the cross product, sine 180 equal to 0. So by considering that, this becomes 0. And from 3 to 4 also, this is the direction of current in this current loop or in this current line. So this is the direction, and the magnetic field direction is, this is the magnetic field direction. They are in the same direction. So that is from 3 to 4 also sine 0 is 0, because in the cross product you are going to get sine 0. Here in the cross product you are going to get your sine 180. So sine 180 equal to 0, and here sine 0 is 0. So finally the force remains with only two integrals, that is from 2 to 3 and 4 to 1. So let us write from 2 to 3 I dl cross B plus from 4 to 1 I dl cross B. So ideal cross B from 2 to 3. Let us consider this is the origin point. If I consider this is from origin point, from 2 to 3 the length will be L, from 4 to 1 L to, this is your origin, so 0. So here we can write from 2 to 3 nothing but that is 0 to L ideal cross B plus 4 to 1, 4 is, that is L to 0 ideal cross B. So ideal cross B from 4 to 1 L to 0 ideal cross B, where dl is nothing but which is defined over, let us consider this is a plane which is defined in z direction. If this plane is placed in z axis, let us consider this is your z axis. If this plane is if this current loop is placed in z axis, then dl becomes your dz. So right here I outside I 0 to L dz and the unit vector is az cross B plus I outside L to 0 dl is dz and the unit vector is az cross B. So the finally here you are going to get F is equal to, that is F is equal to sum F naught minus F naught, because this is from 0 to L. If you have observed here inside the integration dz az cross B, dz az cross B, only there is a change in the limits. This is from 0 to L, this is from L to 0. So by substituting from 0 to L and from L to 0 you are going to get some sign difference. So F is equal to F naught minus F. So where mod F naught is equal to, mod F naught is, what will be the F naught? F naught is equal to, that is I into integration over 0 to L dz, that is az cross B. So dz az from 2 to 3 it is of sine 90, that becomes your 1. So here you can write, so mod F naught, if I consider the mod F naught sine 90 equal to 1, so this is I, this is 0 to L and it is dz, sine 90 is 1, so 0 to L into dz, the magnitude, that is your magnitude of your B, that is B. So I into, so 0 to L, 0 to L is Z, 0 to L and your B, B is your magnitude here. So F naught is equal to I into L into capital B. This is called as magnitude of F naught. Magnitude of F naught is equal to IBL. So let us consider if that plane, so what happens? So in 1 to 2 there is no any force, from 3 to 4 also there is no any force, the force component is equal to 0. Then what will be the direction of this force on 2 to 3 and 3 to 4? The direction of the force will be according to the, so Fleming's rule. So this is the direction of your magnetic field. So this is the direction of your magnetic field and this is the direction of your current. Then the direction of the, according to Fleming's right hand thumb rule, the index finger indicates the magnetic field direction and middle finger indicates the current direction and thumb indicates your force direction. So the direction will be in this direction, the force will be in this direction, that is your F naught. So from 4 to 1 the force direction will be upward. So if you compare in 2 to 3, only the current is Here it is current downward, here the current is upward. If the current is upward, then the force direction will be downward. That is the opposite. So this is the force direction. So the distance between the force is W. This is the F0 downward and F0 upward. So let us consider. So this is the magnetic field direction. So this is your B. And if I consider the force, so which is F0 here and F0 here. So let us consider this is making an angle of alpha with respect to the B, magnetic field. Let us consider. So the plane which is the plane of force which is making an angle of alpha with respect to B, then we can write the torque is equal to, by using this we can write torque is equal to, so torque is equal to mod magnitude of torque is equal to, so magnitude of F0, that is your the value of your F0, and that is the length between it. The length between it is W into sine alpha. But what is mod F0? So mod F0 is equal to I B L sine alpha. IBL sine alpha. So from this we can write IBL sine alpha, that is mod magnitude is equal to IBL into W. IBL into W. So IBL into W into sine alpha. This L into W is nothing but length and multiplication of length and width, that makes you area, that is IBS sine alpha. So here we got T is equal to I into BL sine alpha. This can be written as B I S sine alpha, where IS is equal to M. So where IS is equal to M. So this M is nothing but magnetic dipole moment, where this M is equal to magnetic dipole moment. Magnetic dipole moment. So mod the magnitude of, so B M into sine alpha. So in the form of vector it becomes mod B, that is of the vector B. Here you are having a sine alpha, so cross product with your M. So this will be unit normal to the plane. So M is 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 the magnitude, and unit normal to the plane is M. So T is equal to, this is not mod, this is your vector B and cross M. So here sine alpha is replaced with the cross M. So this is your B cross M. So tau is equal, that is your torque is equal to, it is a cross product of your B cross M. So what will be the unit for your this M? The magnet, that is unit for your magnetic dipole moment is ampere meter square. Ampere meter square. The magnetic dipole moment is a product of your current and the area of the loop. This is your current and this is your I into S. This magnetic dipole moment is the current and multiplication of your area of the loop. So this expression is generally applicable to determine the torque on planar loop of any arbitrary shape through it, it was obtained using the rectangular loop. So here the shape of the rectangular loop, here we have considered a rectangular loop. So irrespective of the shape, so this torque equation is applicable. So the only the limitation is the magnetic field must be the uniform. So this is about your torque. So torque is equal to, that is the cross product of your magnetic field and the magnetic dipole moment. So in the next class we are going to see the next topic, that is your boundary conditions and inductance and inductor. Thank you.